very important in the class. So the motivation today is, I guess, so we will be talking, of course, of stochastic processes. So we need the filtration. That's an increasing family of processes. And I will be always working with adapted processes, meaning that h of t is always ft measurable. Okay. So if I take AS, which is, say, a bounded adapted process, you can define, or let's say in L1, you can define the integral of AS against DS. Just to do it for every omega of your set, it's very easy to define. And you know the fundamental theorem of calculus, which says that if you take phi, which is, say, a C1 function, phi of this thing, yt, it will be phi of y0 plus the integral between 0 and t of phi prime ys as ds. Okay. So what we want to do in this TA is explaining that we can actually change ds in dbs. Somehow we are going to integrate against the Brownian motion. So there will be two things to do. Try to explain what we mean by this, and try to find an equivalent of this. Of fundamental theorem analysis. Okay. So I guess today we can do it together. At least we are going to try. Yeah, just during the whole TA, B would be a standard Brownian motion. Okay. So perhaps somebody who never saw the Ito formula before can answer the first question. So we want to define the integral for a large class of processes. What we are going to do, we are going to define it for simple processes, for the most simplest one you can imagine. And as usual, is the equivalent of step functions. So what we want to consider is a simple process, which is of this form. It's a finite sum of processes like this, Cy of the indicator of Ty plus 1. Where Cy here, because we want the process to be adapted, Cy will be Fty measurable. So you should really think about this class of processes as being the step functions. Okay. So we want to define the integral against the Brownian motion for these processes. Just perhaps to show that there is a difficulty somewhere. Here, you can replace ds by any measure with finite total variation. But it's not the case of the Brownian motion. Brownian motion has infinite total variation, so you cannot just define it brutally. You will do something wrong. Okay, so first, what will be the integral, let's say, between 0 and infinity of this thing? Once again, I apologize for people who already saw that, because that's completely elementary. But what is this integral? What would be a good guess for this integral? Somebody who never saw it. So everybody saw it, perhaps. is a random variable. Okay, so h is a random variable, and I want to integrate it against a random variable. So the good choice for this, perhaps I will not spend too much time, but the good choice for this is c times bt minus bs. Of course, it's really the most natural thing you will define. And for this function, what you will do, because you want your integral to be linear, you just take the linear combination. So for these processes, it's completely elementary to define the integral. So can somebody tell me how you can extend this and to which kind of spaces it would be interesting to extend this process? And we will compare the strategies. Perhaps I didn't take the easiest one to go to Ito's formula. Yes, so this is a definition. You set, it's a random variable.
But independent of the Brownian motion.
Yes, because it's ft measurable. Yeah. Sorry? Yes, so in this case, fs measurable. So that's a random variable. So you define it by linearity. You get the definition for any step process, like simple process. So what you can do and what you want to do usually when you have this is to say my function and think about all the other integral definition. You want to say that this function, somehow there is an isometry behind this function. I have a natural norm to put on this set and a natural norm to put on the target set so that my definition is exactly an isometry. Because if I have an isometry, and if this thing, if I'm lucky, will be, of course, something dense, I can extend by density to the whole set my definition. And it's exactly what I'm going to do. So the natural set is the set, so I will call it perhaps not L2, but let's say E, with the following norm. The norm of a process H will be the integral between 0 and infinity of the expected value of h squared s ds. So that's a norm. I mean, I should perhaps take the square root somewhere, but OK, let's say this is a norm squared. So this will be the starting set, and I will go to the following target set, which is just L2 with a norm 2. So I have two sets, and I want to check that if I take a simple process, which is obviously in this set, if I take a simple process, when I compute the norm of the integral, it's exactly its norm n. So let's take H be a simple process. I want to compute the integral. So I want to compute the expected value of the integral between, say, 0 and infinity of h of s dbs squared. So this is a norm squared, and I want to prove that that's equal to this. OK? Yes? BT minus, yes. BT minus BS is just a random variable.
And sorry, C is a random variable depends on the position in.
So this thing is just a product of random variables.
So C is the random variable depends on other random.
No, the same if you want. You have a probability space. C is defined on this probability space, and B also. So you can make a product that's two random variables which are valued in R, so you can do the product of them. Okay? Everything is defined on the same set omega of random. So I will use this after. No, I will explain this after. But it will not be independent at this point. We don't care. After, it's important, but here we don't care. We can do that for any random variable. Yes, but that's the following step.
FS measurable means that it's
Sorry?
FS measurable means.
No, so the property of Brownian motion makes that it's independent, but not the fact that it's Fs measurable. So you will see. So here's the definition of the integral gives you that that's equal to this. And when you develop the product, so I have the impression that everybody knows. So, no? Okay. Thanks. Even if you didn't believe it, thank you for that. Okay. So when I have this big square, I can expand it. So I will have some terms where I take I in the first sum and I in the second sum. So these terms are exactly of this form. That's the term where I take both the same points. And I have other terms, actually a lot of them, where I don't take the same index in the first and the second sum. Okay? So this is trivial. And so now I'm going to use, indeed, properties of the Brownian motion here, because there are many, many things that cancel, so that are actually equal to 0. So in this big sum, where I have of order n squared terms, actually they all vanish. Why is it true? Because all these three random variables, they are f t j minus 1 measurable. By definition, because y is less than j. But as you said, a Brownian motion, it has independent increments. They are independent of what is happening before, and they are centered. So when I'm looking at this sum here, when I'm taking the expected value of this product, since this is independent of that and has 0 mean, it implies that this thing equals 0. So when you look at this, this is if you prefer this. And this is 0. Okay, so that's the first property of Brownian motion we use here. The fact that that's a martingale. And the second thing here, when I'm looking at this, if I write too fast, I have corrections anyway on my web page, so I don't know if it's worth spending too many time to write. So you do the same thing, and here you get the expected value of b ty minus b ty minus 1 squared, knowing f t y minus 1. And this thing, properties of the Brownian motion, this is ty minus ty minus 1. So really, for people who are scared by these two properties, you come at the end and you ask me. Okay? That's two properties, very basic properties of the Brownian motion. So nothing deep here. So I can let the ti minus 1 go out of my expectation. And when I get here, all these things are actually equal to 0, and all these things are just the sum for e equals 1 to n of ty minus 1 times the expected value of cy squared. And when you think about that, this thing, it's exactly equal to that for the step function. So this thing is exactly equal to the integral between 0 and infinity of. Yes? No, because here there is two different indexes. That's just not pedagogic. Well, that's the only thing. But you need to be measurable. No, but here there is an index which is not the same as here. The y is becoming y minus 1, just to confuse you, because you know everybody knows, so like this. So no, the important thing is that this one must be measurable with respect to the left side of your interval. Okay? So this thing, I just let you as an exercise, just that's exactly what is written there. So basically, if I call, say, T, this map, which take C, which take, which take a simple process and associate the integral, it's just an isometry. We have that the normal 2 of T of H is exactly the norm of H. Okay? And it's very easy to check that these simple processes, they are dense in a lot of spaces, and in particular in E, so that you can extend by linearity your process to the whole space E. So now, what I have defined, very, it's a non-constructive proof somehow, but I have for every process H which satisfies that the integral between 0 and infinity of this is less than infinity, I have defined an integral with respect to the Brownian motion. I have defined this, which is a random variable. And I know that its norm is equal to this. Norm 2 is equal to. OK. So now I will look at another class of processes, which are even simpler, is that bounded processes. You will understand, I mean, here the definition is somehow hidden by this fact that we extend the definition by just density. But you will see after that we can come back to really an approximation principle where we see what we are doing. But first, let's consider bounded processes, and I will define the integral between 0 and t of a process, just to be the integral between 0 and infinity of the indicator times h of s. And this is well defined because this thing obviously satisfies this. OK? So now I have an integral for any bounded adapted process. I have an integral with respect to Brownian motion. And the first property, which is non-trivial, is that this process, that I will call MT or YT, it's a martingale. Okay? So when you have defined an object like this, and you want to check a property on it, you don't have any choice. You start from where it's explicit, where your definition is explicit, and after you check that it extends to the other cases. So we are going to just check it for the case where you are a step function, a simple process. We are going to check that the integral in this case is a martingale. But checking for step processes is actually equivalent to checking only for this process. Why? Because a sum of martingales is a martingale. So in this case, we need to check that the process we define, which is, so the integral between 0 and t, so s and t will be replaced by u and v, because I want t to be the time. So I need to check that this thing is a martingale. And this thing is exactly this thing. Okay? Well, I'm not going to do all the cases, but let's take A and B that are, so let's take, sorry, S and T that are between U and V, and let's check that we have the expectation of YT knowing Fs, which is equal to Ys. Okay? I should do the other cases but it's exactly the same. It works always the same. So in our case here, Yt, when it's like this, it's C Bt minus Bu. You can check it from the definition. Ys is Cys minus Yu. Bs minus Bu, sorry. So when I look at the expectation of Yt knowing Fs, it's exactly the expectation of this horrible thing. And now, C, it's Fu measurable. So in the expectation, it can get out. The C can go here, because it's in particular Fs measurable. Bu also, and it remains this Bt knowing Fs, but because the Brownian motion is a martingale, Bt knowing knowing Fs, sorry, is exactly Bs. So this thing, it's C times that's exactly C Bs minus Bu. And Bs minus C times Bs minus Bu is exactly Ys. Okay? So in this case, it's completely straightforward to check that it's true. So by linearity, it's completely straightforward that that's true for simple processes. And how do you go to all the processes that are integrable? Just by continuity of the norm. When actually the property to be a martingale is stable by limits with respect to these norms. Okay? So that's a martingale, this process. So, I mean, you start by a definition which is definitely not very intuitive. I mean, for stable processes, that's obviously what you want to do, but after you don't know what it does for square integrable processes. But step by step, we are going to understand it better. So now we know that that's a martingale. And actually, it's not hard, but I will not do it to prove that YT admits modification, which is also continuous. So YT can be admits a continuous modification. So what do I mean by that? I mean that the YT that I define like this has no reason to be continuous. Because when I extend my map, there is no reason that the piecewise paths are continuous. But it appears that it's still a martingale, and when you are in martingale, you have the Doob inequality, and working a little bit with the Doob inequality, you can prove that because the YT in the case of simple processes are obviously continuous, then you have something continuous. So if you don't understand this, I mean, that's not very important. Just say that actually you can take it to be continuous, this process. And you can check that in the case of step functions, of simple processes, it's the case. It's obviously continuous as linear combination of Brownian motion, which are continuous. Okay? It's exactly like when you define your Brownian motion. First, you define it. I don't know what is your favorite definition, but you can define it like a Gaussian process, and after you need to check something to check that you can have a modification which is continuous. So this part, I will not explain it, but the conclusion is that YT is a continuous martingale. Okay. So that was the blah blah. Now let's see how you handle this kind of process. How you can have an intuition about this kind of processes. So just for this question, I will assume that AS, so that HS is continuous. So it's continuous, it's still bounded, and it's adapted. Okay. I want to approximate this process because so far I don't understand what it does exactly. So I'm between 0 and, say, t. I want to descend it between 0 and t. And I'm going to take a partition, a sequence of times, such that the first time is 0, the last time is t, and say the steps between two adjacent times is small, is tending to 0. So let's take, I don't know, something like this. Let's say you have n points. You can just take the n, the natural partition. Okay, the property is that the integral between 0 and t of edge of s dbs is just the limit when n goes to infinity, and the limit is in L2. So for the norm 2, if you prefer, of the sum for e equals 1 to n of edge of ty, bty minus bty minus 1. Actually, that's just that. Okay? Exactly like a Riemann sum, which approximates your integral. That's the same thing, just that instead of having ty minus 1, you have bty minus bty minus 1. Okay? So how do you prove this? Actually, you have nothing to do. You have really nothing to do, because this thing here, the second term, it's the integral between 0 and t of some process, h s that I will denote n, where h s of n is the sum of the h ty indicator of ty minus 1. By definition, this thing is exactly the integral of that. So if I want to prove that this thing converges to that in L2, because that's an isometry, I just need to prove that this thing converges for the norm to H. But that's obvious. You have a continuous bounded process. Of course, the step functions are converges to H. Okay? So this property is completely trivial, and if you want to have an intuition of what is your process, you should really understand it like the limit of this thing, which is natural. Okay? Okay, let's look at another thing. Look at the limit now, when n goes to infinity, of the sum between y and n of HTY still. But this time, I'm going to take this thing. I'm going to square. Obviously, in the case where BTY is, in the usual case that you are used to, where it's TY minus TY minus 1, this thing goes to 0. Do you agree with that? Because if here you have ty minus ty minus 1 squared, it's of order 1 over n squared, and you sum n terms like this, so you get something of order 1 over n. But in our case, it's not the case. It's not what happens. In this case, this thing is converging to this. And this property, which is very, very different from the usual one, is exactly what will make the difference between the standard fundamental theorem of analysis you know and this one, where you have obviously the same term here, but you have an additional term that you don't understand, which is arising here. This term is exactly arising from the fact that the second order in your development is not going to 0. Okay. So if you want to prove that, I will not do it, but that's not hard. You just say this thing here, it's not hard to prove that that's the limit of this. So basically, you want to prove that this sum minus this sum goes to 0, converges to 0. And what you are going to use here is the fact that this minus this is the increment of this process, bt squared minus t. And this process is also a martingale. So exactly like, so I erase the computation I did here, but remember, there was this huge sum of n squared terms, and I said there is n squared n terms that are relevant, and n squared minus n terms that are not. And these n squared minus n terms are very annoying. And usually it's where you have all the weights. But in the case where you are martingale, these cross terms, they disappear. All of them are equal to 0. So you are just ending with n terms. And these n terms, so imagine here you should have n squared terms of order 1 over n squared. So you are of order 1. But because there is, for free, this n squared minus n terms that disappear, you are just ending with n terms of order 1 over n squared. So this thing converges to 0. Yes?
I don't even know what that means. I thought that this was a vector.
What is a vector? No, so you have your Brownian motion, and it's just here, that's a real number. Is that the difference between? Yeah. So what I'm saying is that I must prove that this difference goes to 0. So yes. Yes, but BT minus BT, BTI minus BTI minus 1 is not of order 1 over n. That's the thing. It's typically of order 1 over square root of n. That's the thing, yeah. That's really different from the ty minus 1. That's not of order 1 over n. Sorry? Because there is an averaging happening naturally by the fact of your Brownian motion. This definition is non-trivial somehow. But what I want you to keep in mind is really that this term is not going to 0. So now we can prove, or at least sketch the proof of Ito's formula. And after, we will use it in a special case. So I want to prove, so Ito's formula is saying exactly, is exactly extending my, my fundamental theorem of analysis by saying now I take y, which is not the integral with respect to nice measure, but something where I have a term in dB, and just because I will need it later, I add a term which is a nice term with an integration with respect to something which has bounded variation, just because it will be useful. And as before, I want to express phi of yt minus phi of y0 in terms of this integral of phi prime, the integral of phi prime. But because of this annoying term, or not annoying, depends what you like, you need to go a little bit further. You will need to go to the next step. So it's why we will require the function phi that you look at to be C2. OK? And then you get this formula, which so far, I guess, is not very entertaining, but which will become a little bit clearer, I hope, later. So phi of yt minus phi of y0, I will mimic what I will do for usual usual functions. I'm going to write that the sum between y and n of phi of y ty minus phi of y ty minus 1. OK? I sum the increments. And usually what I do here is that I'm writing this as phi prime. I use Lagrange theorem to say that phi prime of y ci bti minus bti minus 1. Sorry, yty plus yty minus 1. The problem is that if you stick to this, this level, this second order term will not vanish, and this will not converge to the right thing. You will not be able to handle this thing. So what you want to do is simply to write Lagrange theorem at the second order. So it's this thing plus 1/2 phi double prime of y cy y ty minus y ty minus 1 squared. And this cy, it belongs to ty minus 1 ty. Okay? I try to mimic the usual proof, but I know that there will be troubles with the second order term, so I add a term. Okay, so we have basically two terms, two big sums. We have this sum, and the other one on the left. So I will first handle the sum on the other one on the right, sorry. I will handle the first one. So I have this thing. Okay, let's try not to switch every time. And I want to look at the limit of this when, so here I forgot that it's depending on n. So here there is a dependence in n, obviously. I mean, that's ty of n that I forgot since here for my own good. So here this n should be written everywhere. Okay. So what is that first? This is the integral between 0 and t y n of as dbs plus sigma s ds. That's the definition of yt. And the second thing is exactly the same thing up to time ty minus 1 n. So, you know, instead of writing the difference, you can just write that that's equal to this. Okay? Okay. So now we know I didn't assume here that A and sigma were continuous, but if you manage to prove this formula for A and sigma continuous, it's very easy by limit to prove that, and density to prove that that's true for any bounded process. You just take the limit here and on this side, and everything is continuous with respect to the norm that you are looking at. So I will assume that A and sigma are continuous. So here, ty minus 1n and tyn, they are pretty close. So as and sigma s are almost constant here. So this thing is exactly equal. I mean, it's better if I write this like this. I will say that the as minus a ty minus 1n dbs plus sigma s minus sigma ty minus 1n ds plus I subtract and I integrate things. So I just subtract and sum these two terms. Did not do anything nasty. So this thing is the sum of terms of this kind and terms of this kind. So terms of this kind, if I rewrite them, it's exactly equal to this. Phi prime of y ty minus 1n times, say, for this one, a ty minus 1n times b tyn minus b ty minus 1n, plus another term. This thing, what do you recognize? You just recognize this sum here. But exactly the same thing applied to this edge. So this thing here, it converges when n goes to infinity to this thing. It's just what I proved earlier. This thing is exactly the first term here. Okay? When I'm looking at the second term here, so there is this term times this. That will be a sum of this thing, and using, once again, an approximation principle, this thing will converge to this. Exactly for the same reason, the dBs is this time a tyn minus ty minus n. So that's really associated to the measure ds. And this is exactly the second term here. Okay? There is this term that I didn't look at so far, but when you look at it, you see that's an integral against dBs, but of something which is tending to 0. And that's actually very, very easy to show that this thing is tending to 0. And same thing for here. So this term does not contribute. Very, very elementary to do it. So from my first term, which is a natural term, the same as in the usual case, I get exactly the two terms that are corresponding to the usual case, to the phi prime. But I have still this term. And this term will arise from the second term. So the second term, of course, I'm not going to do the whole computation, but give you a hint of what is happening. So what I did here, I replaced this thing by this, morally. Just saying that because A and sigma are continuous, they are almost constant on this small interval ty minus 1, so that I can replace this thing by this thing. So you will allow me to do exactly the same thing for the second term. So the second term this thing, I will replace this by a ty minus 1 b ty minus b ty minus 1 plus the term in sigma. And it's squared. So when I'm developing this squared, what I get is I get this thing squared plus this thing squared plus a cross product involving the two terms. So this term here and these terms, they are small. When you think about that, let's say this term is already of the right order. So when you multiply it by something tending to 0, you will get something that will vanish. So this term will disappear. This term also, because that's the right order square. So this term will also vanish. But this term, as we have seen earlier here, it does not vanish. And it exactly corresponds when I do the sum. So by continuity, this thing is almost this thing. So you still have things to check, but that's true. Here you see that that's the convergence there for this thing. So of course, there is a 1/2. Yes. So this thing is converging to the integral 1/2 of the integral between 0 and t of 5 double prime of ys, as squared, and ds. And this is exactly the third term. Okay? So really what you have to keep in mind is that there is an additional term, which is not intuitive, but actually very natural when you think that this second order for b does not vanish. And after the proof, finally, is very simple. It's just mimicking exactly what you do in the case of normal processes. So now you can do many variants of that. You can add, say, a time t here. So it will be 0. And you will have usual terms that, I mean, the relevant terms that you need to add will be obvious to you. So really, the main part was to understand why this new term appears. And that's really because the quadratic variation of the Brownian motion is t. Okay? So, two things. The integral against the Brownian motion, it gives you a continuous martingale, first thing. Second thing, Ito's formula. So, which is exactly the same as before, but you need to add this new term. Just to know, of course, bounded is not the best thing you can do. You can do a lot of other things that are more natural, but the proof gets messier and messier. And the Brownian motion is not the only thing you can integrate against. What did we use for the Brownian motion? That it's continuous, that it's a martingale, so you can integrate against any martingale a priori, and we use bt squared minus t is a martingale. So actually, for any martingale m, you have a process which is increasing, such that mt squared minus this process is a martingale. And what you will need to do is to replace this ds by the derivative of this process. But the proof will work the same. So you can integrate against a large class of processes, semi-martingales, and it gives you always the same thing. I mean, the magic thing was this squared here. Okay, so I have 20 last minutes, I guess. So I will talk a little bit, but really a little bit, about Bessel processes, because we will need them in the remaining of the class. So if it was too fast for some people, you can come and ask me. Of course, I know that nobody will come, but I will be happy to answer again. Yeah. So just when you write this, it's not very convenient. I mean, it takes a lot of place, even if you have, in addition, if you have this. So usually this thing, we just say that that's equivalent to writing this thing, but that's just a convention. I mean, this thing doesn't mean anything, but we usually write that that's equal to this. And y0 equal x. So that's a differential form, a notation, just shorthand for this. Okay? So we will be using that every time. But you just have to keep in mind that something solving that is exactly meaning that. Nothing more. So no black magic behind this. Okay. So the Bessel processes, it's a process such that x0 equals x, say, a real positive number, and such that, and you will see it becomes more complicated. Such that this thing satisfies exactly that. So the xt is on both sides of the equation. But it only means that when you look at it as an integral, xt is equal to x plus the integral between 0 and t of dbt plus the integral between 0 and t of this. So it's not completely obvious that it exists, but trust me, it does. And that's the Bessel process of dimension D. So why dimension? Because actually, when you take D to be an integer, when you look at the norm of a vector with D Brownian independent entries, this is exactly the law of that. This is exactly this process. Okay? So at least for integer, yes? So you take a d-dimensional vector from which all the entries are normal, are Brownian motion, then it gives you this process. It's not completely trivial, you have to check. Okay, so that's a very important class of processes because from this thing, they satisfy exactly the same rescaling property than the Brownian motion. If you delete it, okay, so I always I'm always confused, so is this something like this, I guess? I never know, perhaps that's t squared and t. Well, it has the same property with x. And actually, that's the only continuous processes that have this property. Martingale. Okay. So what I want to do now, so that's a positive process, you see, which is pushed from 0. When you get close to 0, this dt is becoming bigger and bigger and is pushing you back on the positive, on the upper side. So basically, your process is doing that, and when it goes closer to 0, it bumps. So actually, it's not clear that it does this, but you can imagine at least that for very big D, the push is that strong that you will never hit the origin. Now, if you take D very small, there is no reason why it should not hit the origin. And actually, for D smaller or equal to 1, there is no push anymore. So for small d, actually, it will touch the origin before. So it will be killed at the origin. What I want to do, and I don't know if I will have time, is to try to know where is the transition between the time where it hits the origin before infinity and when it doesn't. Okay? And in order to do that, what I will do is that I will explicitly compute the probability that this Bessel process exits from A, the interval AB, for A below x and B above x. Because this thing will exactly tell you how much you want to go down. Okay? So this thing, I will call it phi of x. That's the probability starting from x that the process exits this interval by A. So tau is the heating time of the exiting time or heating time of AB. And you will see that this Hito formula is very, very convenient for that, for computing such a thing. And if you don't like this proof, you will really don't like the next proof for SLEs, because it will be always the same kind of thing that we will do. So we have a diffusion just means something solving this kind of stuff. And we are trying to compute the probability of exiting an interval. And the trick here is that phi of x t, but just before it exits the interval, so t inf tau, it's a martingale. And why is it true? I don't want to enter into too many details, but that's because it is. I don't know. So it's a martingale against this filtration. So this is due to the fact that X is a martingale. Do I want to explain that or not? Because I need really to do. OK, I don't explain that. We will have the opportunity to go back to this later. Because I really want to finish, and I have only 10 minutes. So this thing is a martingale. Trust me. So now what I want to do is to use Ito's formula. And how can it help me? Because, you see, what did we say? We say that this thing here is automatically a martingale. It's what we prove. The integral against the Brownian motion is a continuous martingale. So if I assume, let's assume that phi is C2, then when I will use Ito's formula, I will have this thing which is a martingale because, so I will have this thing which is a martingale, this thing which is constant, so it's a martingale, this thing which is a martingale, so what do I deduce? That this thing is a martingale. But this thing doesn't like to be a martingale because this thing is an integration against ds, and it's not very hard to prove that something of bounded variation, so this is something of bounded variation, it cannot be a martingale. It must be 0 if it's a martingale. Somehow martingales, they always have a non-trivial, an infinite variation. The right order to look at for a martingale is for square, for the second order, exactly like in the case of the Brownian motion. So if you look at the first order, it will explode. So what does it mean? It means that this thing equals 0. Start to be really, yeah. So if phi is C2, because I have all these martingales in the Ito formula, I have the last term, which must be a martingale. So we must have that this thing. So what is sigma s in our case? Sigma s is this thing. So it's d minus 1 over 2. So that's xs plus 1/2 of phi double prime of xs. And what is as in our case? It's just 1. So I must have this thing, which is a martingale. And because I just say that a martingale with bounded variation is necessarily equal to 0, this thing must be equal to 0. Phi. So phi of x is the probability starting from x to exit this interval at time from A. Sorry. Tau is a hidden time. Yes, that's a random variable. The thing is that I want it to be A and not B. It's at a random time that I don't know, or I know it, as you prefer.
But phi sooner or later will touch A, or you want a specific value?
No, sooner or later we'll touch A, and perhaps I should have explained why, because of this scale invariance, which is true for X. You cannot stay forever in this narrow tube because you are scale invariant. So I get that this thing equals 0. And this this diffusion, actually, it's a very continuous diffusion, and it can do whatever you want. So in order for that to be equal to 0, it must be that phi prime of x d minus 1 over 2x plus phi double prime of x equals 0. There is a 1/2 here. Somehow, it does not depend on the xs inside. It must be 0 anyway. And that's the reason is that this xs can take all the value you want, perhaps with very small probability, but it can take whatever value. So if you want really this process to be equal to 0, for every t, you want that this process equals 0 for every s. But because xs can have whatever value, you really want that this equation, to be satisfied. Okay, but this equation, I can solve it if I have boundary conditions, and the boundary conditions are easy to get. Phi of A, if I start from A, I exit instantaneously from A, so phi of A is 1. And phi of B is 0, because I just exit the domain, but not from. Sorry? Yes, for all y, if you want, between A and B. True. Because x can go to whatever value between A and B. Yes. Okay, and this you can solve it. And let's say for d greater or equal to 2, you get that phi of y is equal to to b to the 2 minus d minus x y to the 2 minus d over a to the 2 minus d minus y to the 2 minus d. For d less or equal to 2, so for d not equal to 2, and for d equals 2, you get something with logarithm. But I mean, you know how to solve such an equation. Okay. So now, the only thing which remains to do is to really get rid of something I assume, which is this. This has no reason to be true. I mean, I assume it, you trust me, but no reason. And that's where the technique is very, very nice, is that in the opposite direction. Now I take, so just I will switch, I will call this 5, 0 of y. Just to have, this was in my head, and now I just assume that I know that. All this part here between this and this was completely in my head. I forget completely about it, and I just remember the value there. So I didn't assume anything, I just have a function. And now the thing is that I want to connect this function to this, but if I look at 5, 0 of xt inf tau, I can use the tau formula. And what will I get? That this term equals 0. So I only have these terms. And these two terms, they are a martingale. So phi 0 of xt and tau, it's a martingale. And actually, I have even better than this. That's a continuous martingale. That's also a bounded martingale. Why? Because phi 0 is between 0 and 1. And moreover, what do I get is that at infinity, when t goes to infinity, phi 0 of xt of tau, it converges to exactly the indicator of xt and tau if x tau equals a. So this is due to the boundary conditions. I mean, when t goes to infinity, when I look at this applied to xt and tau, at some point, I'm going to exit the domain. If I exit at a, I will exactly be equal to 1. If I exit at b, I will be exactly equal to 0. So basically, when t goes to infinity, this thing is equal to that. OK? So now what do I have? I have two martingales, phi of xt and tau and phi 0 of xt and tau, which are two martingales with the same limit at infinity. They are both bounded, so using the stopping time theorem, you deduce that they are equal. So really, in this last step, the important thing is that they are bounded. So by stopping time, and that will be the end, by stopping time, we deduce that phi of xt and tau is exactly equal to b to the 2 minus d minus xt and tau to the 2 minus d over something. And now I can use the fact that I'm a martingale. I take the expectation, and I get that phi of x is indeed equal to phi 0 of x. So the philosophy is that I didn't need to assume that phi is C2. I just have, if I was a magician, I would just pick the phi 0 and tell you phi 0 of xt and tau is a martingale with the same boundary conditions as my martingale I'm looking at. So they are the same. That's just the philosophy. So this part is not important. OK, just for the story now, I have phi of x. So if I want, and I will let you that as an exercise, for instance, to prove that for d greater than 2, I never hit the origin, what I do is I look at this. When t is greater than 2, 2 minus d is actually negative. And I can let b goes to infinity, or perhaps a. No, you let a goes to 0. It has a limit. This thing will converge to a real probability, which is exactly saying you touch b before 0. I saw it. I just finished. So it will say you touch b before 0 with, say, probability, I don't know, 6 or 7, and you let b goes to infinity, and it exactly tells you that 6 or 7 for probability, perhaps a little bit too much. But you never know. I mean, I'm working with complex probabilities, and you see it's making me mad. Anyway, so 0.6 or 0.7, and after you let b goes to infinity, which is exactly saying that you will hit any positive number before 0. So you will never hit 0. OK, that's a very simple exercise I left to you. For d greater than 2, for d equals 2, you can do exactly the same thing. But for d smaller than 2, you can do the opposite. Prove that actually you will touch 0. So the difference, really, the threshold, the transition, is d equals 2, which is exactly corresponding to the two-dimensional Brownian motion for people. And yes, that's already too much. Thank you. Oh. Do you still want to ask your question? No. Oh, at the bottom, yes. Yes. Here it's B and here it's A. I mean. Yeah. Yes. So how it? Yes. Yes. There is an absolute I mean, the norm will be the absolute value of that. In dimension 1, the norm of the Brownian motion is its absolute value. Yes. So it will be always positive because it will be exactly the absolute value of one single Brownian motion. Yes. So actually, so here I was just saying that you kill it when it touch. After you can study if you can make it bump or not, and that depends on D. Okay, thank you.